Hi everyone, my name is Michon and I'm a researcher at Grab. In this presentation, I will give you an overview of the work that has been done by the Faust team around embedded systems for real-time audio signal processing and Faust. The computer music and music technology communities have been greatly impacted by the advent of the makers and DIY communities in recent years. In this context, embedded audio systems have been increasingly used to create musical instruments, sound effect processors, art installations, or even to prototype and commercialize products in the music technology industry. I'm thinking, for example, of the Moduo company. In parallel of that, mobile devices like smartphones, tablets, etc., which in some respects can also be considered as embedded systems, have been used for similar types of applications. Embedded Linux systems, such as the Raspberry Pi or the BeagleBoard, were the only available solutions accessible to the aforementioned communities for a long time. Linux allowed them to deal with embedded audio processing in the same way than on a desktop computer through the use of high-level tools like PureData, Chuck, supercolliders, etc. Specialized Linux distributions with specific configurations for real-time audio processing, such as Satellite Karma, were also developed in this context. However, the ease of use offered by operating systems come at the cost of lightness and simplicity, audio latency, and efficiency. Moreover, most of these boards were often not designed with real-time audio applications in mind, and lack a proper audio output, implying the use of an external audio interface. More recently, these issues were addressed by specialized hardware and software solutions such as the Bella, which was first released in 2014, and the ELK. In both cases, dedicated hardware is added to standard embedded Linux systems like the Raspberry Pi for the ELK and the BeagleBone Black for the Bella to improve their performances for real-time audio processing applications. These products work in conjunction with specialized Linux distributions where audio processing tasks are carried out outside of the operating system, allowing for the use of significantly smaller buffer sizes and therefore lower audio latency. While this type of solution offers a good compromise in terms of ease of use and performances, it remains expensive, like $239 for the ELK and $200 for the Bella. And they are relatively heavy for the kind of application it usually targets. Even more recently, new generations of microcontrollers, such as the ARM Cortex-M family or the ESP32, have been offering extended computational power, like 600 MHz for the Cortex-M7, suitable for real-time audio processing applications. Many of these microcontrollers also host a floating point unit, greatly simplifying the implementation of DSP algorithms. Some microcontroller-based boards, such as the Liligo TTGO T-Audio, provide a comprehensive solution for real-time audio processing applications by hosting an audio codec and an external RAM module. Other brands and boards, like the Teensy, distribute an audio shield, which is essentially a breakout board for an audio codec with the correct form factor to be mounted on the main board. Programming microcontrollers for real-time audio signal processing application is a more complex task than on embedded Linux system because the use of C++ is always required at the end of the toolchain. There also exist specialized chips such as digital signal processors, and they also became more accessible in recent years by allowing the use of floating points and C++ for their programming, while assembly and fixed point used to be the norm. Analog devices, SHARC processor family has been dominating the floating point DSP market for many years now, and can be found in a wide range of commercial synthesizers like Korg, Roland, etc. And evaluation boards for this type of chip, such as the SHARC audio module, now also try to target the markets and hobbyist communities by making their programming toolchain higher level and also more accessible. Okay, so that's it for the background. Let's now look at what role Faust has to play in this world. Embedded Linux systems offer more or less the same type of features as desktop Linux distributions. Thus, real-time audio signal processing tasks can be carried out in many different ways on this type of platforms. For instance, standalone applications can be made and connected directly to various audio engines such as ALSA, Jack, etc. Open source computer programming environments like Perdata, Chuck, SuperCollider are also available. Various audio plugin hosts like Ardor and Audacity can be used to execute audio plugins. And finally, while not necessarily the best and most effective option in that context, web apps can potentially be used as well. A detailed overview of these various architectures is provided in the paper itself, so I recommend you to just have a look at it at this point. While most Linux-compatible Faust 2 compilation scripts can be used on embedded Linux systems with potentially some adjustments in the C++ compilation flags, platform-specific scripts such as Faust2 RPI ALSA console or Faust2 RPI NetJack console, which target the Raspberry Pi, were implemented. Even though Faust can generate applications with a user interface like Qt and GDK, you know them, right? These don't necessarily make sense in the context of embedded systems where screens are not always used or available. Hence, functionalities are typically accessed through SSH, making command line applications more appropriate in that context. Designing musical instruments around embedded Linux system also implies the use of an external microcontroller, which is usually either connected through USB or I2C, since the CPUs used on these platforms don't have built-in ADCs. External controllers like MIDI controllers or communication protocols such as OSC can be used as well with Faust, but it defeats the purpose in this context by externalizing some parts of the instruments. A series of projects and commercial products such as the Bella and the Elk have been trying to provide dedicated Linux-based platforms for musical instrument design, real-time audio signal processing applications. Both are based on existing embedded Linux systems and involve the use of a sister board or hat and of a specialized Linux distribution in order to provide high priority to audio processing, bypassing the operating system through the use of Xenomai for reduced audio latency, multi-channel audio codecs, built-in microcontrollers for analog sensor inputs, etc. So they provide you with additional features to what you would get on a normal embedded Linux system. Faust can be used for audio programming on the Bella with Faust Bella. This command line tool takes a Faust program as its main argument and executes it on this board by running Faust Bella blah 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 blah. Just look at the options in the help for this script. MIDI and polyphony support can be enabled by using the -MIDI and -envoices options respectively. The parameters of the Faust program can also be accessed through a web interface running on a dedicated built-in web server by using the -GUI option. Okay, so while the Elk is not officially supported by Faust through an architecture file, Faust objects can be compiled as VST plugins compatible with the Elk. In that case, you want to use Faust to Faust VST, and Elk also provides a CMake file to carry out this task. Mobile platforms can be considered as embedded systems as well. In particular, musical instruments can be easily constructed around these platforms through the use of microcontrollers connected to them via MIDI with USB or Bluetooth. And yeah, Faust played a pioneering role in the field of mobile music by allowing for the programming of iOS and Android devices for real-time audio signal applications for a very, very long time now. So on one hand, you have Faust to iOS, which is a tool to convert Faust programs into ready-to-use iOS applications, whose user interface is based on the UI description provided in the Faust code, just like most Faust architectures. User interfaces are therefore typically made out of sliders, knobs, buttons, groups, etc. You know Faust. Well, at least I hope you do. The slide here that you can see on the screen is a screenshot of SF Capture, which is an app made with Faust to iOS as part of the Smart Faust project. If you don't know about this project, you can just go on the Faust website to know more about it. So Faust to iOS works as a command line tool taking a Faust program as its main argument and producing either a ready-to-install iOS app or the Xcode project corresponding to the app in return. Various features can be added to the generated app, such as MIDI, OSC, and polyphony support simply by using specific flags when running Faust to iOS. Regular Faust options are also available to generate parallelized DSP code, change sample resolution, and any parameter of a Faust program can be assigned to a specific axis of a built-in motion sensor like the accelerometer or the gyroscope of the smartphone simply by using metadata, which is pretty cool. Complex nonlinear mappings can be implemented using this mechanism, so we really worked hard on that kind of stuff. Faust to Android is the equivalent of Faust to iOS, but for the Android platform, and can also be used as a command line tool. It provides more or less the same features as Faust to iOS. On the other hand, unlike Faust to iOS, standard Faust user interfaces can be replaced by advanced user interfaces more usable in a musical context, such as piano keyboards, XY controllers, etc. Okay, we also have Faust to Smart Keyboard, which is a command line tool that can be used to generate iOS or Android apps where the standard Faust user interface is completely replaced this time by a more advanced interface, better adapted to use in a live music performance context and touchscreens in general. This type of interface uses the Smart Keyboard system, which is a highly configurable keyboards matrix where keys can be seen both as discrete buttons and continuous XY controllers. For example, a keyboard matrix of size 1 by 1, which is basically a single keyboard with a single key, will fill up the screen, which can then be used as a multi-touch XY controller. The interface can be configured directly from the Faust code using metadata. That's usually how it works in Faust. Okay, let's now talk about microcontrollers. First, the OWL is a series of programmable hardware, guitar effect pedals, modular synth modules, etc., developed by Rebel Technology for real-time audio signal processing. The OWL is based on an ARM Cortex M4, which is a microcontroller providing an FPU. Remember what I said about FPU earlier in this presentation. The OWL is the first microcontroller-based platform that was programmable with Faust, which is why we're showing it here. Faust support is relatively basic on this platform, and running Faust to OWL will generate C++ code usable directly within the OWL toolchain. All right, so I'm sure you all know about this one at this point, but Teensy is a family of microcontroller-based prototyping boards developed and distributed by PJRC and targeting the makers community. Just like the OWL, Teensys are based on an ARM Cortex-M microcontroller, which in some cases, like for the Teensy 3.6 and the Teensy 4.0, host an FPU, ensuring compatibility with Faust. Once again, we can only generate floating point C++ code with Faust. PGRC also distributes an audio shield, which is essentially a breakout board for an audio codec, and in that case it's the SGTL 5000, if I remember correctly, compatible with most Teensy boards. This allows us to add a proper stereo input and output to the Teensy. Faust has been supporting the Teensy for over a year now through Faust to Teensy. Various optimizations are carried out to take advantage of the Cortex-M architecture. Because of the limited amount of RAM on the Teensy, Faust only provides basic features for this platform. For example, polyphonic objects cannot be created yet. As an example, the Teensy 4.0 is based on a 600 MHz Cortex-M7 with 1024 kilobytes of RAM. And up to 650 wavetable-based Faust sine wave oscillators can be run on it in parallel, providing enough computational power to run most standard DSP algorithms. If you can run 650 sine waves in parallel, you can run a lot of other things. And the cool thing about the Teensy is that it only costs about $20. Okay, then the ESP32 is a microcontroller designed and produced in China by Espressif. Its dual-core architecture is based on an Extensa 32-bits LX6 microprocessor operating at 240 megahertz and with 512 kilobytes of RAM, and also provides built-in Wi-Fi and Bluetooth support for an unparalleled price, only $3. Yeah, very, very, very cheap. The ESP32 has been used at the heart of a series of prototyping boards targeting real-time audio processing applications, like adding audio codecs, SRAM modules, etc., such as the Liligo TTGOT audio board, which you can see here on the picture, and they all can be programmed with Faust through the use of Faust to ESP32. Drivers for various audio codecs are supported by Faust to ESP32 and can be targeted through the use of options when you call that script. Recent developments involve MIDI and polyphony support using the onboard Wi-Fi. OST over UDP can be implemented, and also Bluetooth MIDI, which is a very recent feature. Additionally, the Liligo TTGOT audio can now be fully programmed with Faust without writing a single line of C++ code or Arduino code. In that case, metadata can be used to access the various analog inputs and GPIOs of the board, and that's what we do in the case of the gramophone. If you never heard of the gramophone, just visit the Gram website, and you should be able to find it very easily. It's programmable musical instruments, programmable with Faust. Okay, the SHARC audio module can be targeted with Faust as well, using the Faust to SAM command line tool, which converts a Faust program into a C++ package, which can be inserted into a project on the cross-core embedded Studio bare metal framework. Despite some efforts in that direction, this platform doesn't necessarily target the hobbyist maker communities, and the toolchain remains relatively cumbersome, unfortunately. For example, a USB JTAG emulator, such as the analog device's ICE1000, must be used for its programming. Moreover, Faust objects running on the SHARC audio module can only be controlled using MIDI through a physical MIDI connector, which can be very limiting in many cases. We'd like to support other types of digital signal processors in the future. In particular, being able to target fixed point chips would be a huge step forward, just to help make this type of platform more accessible. All right, so where are we going with this now? So while microcontrollers existed for decades before Arduinos, it's only when this platform appeared about 15 years ago that they became fully accessible. The Arduino IDE programming environment played a huge role in that context by offering a high-level way to program these low-level platforms. Our conviction is that domain-specific languages such as Faust can make low-level platforms with potential applications for audio processing more accessible to the makers, audio DSP, and music technology communities. We mean FPGAs, GPUs, and bare metal CPU-based embedded systems when we say these platforms. Such systems can target ultra-low latency applications and provide extended computational power for specific algorithms. So our future efforts will focus on these topics, and let me give you more details about that. So CPU-based embedded Linux systems such as the Raspberry Pi provide extended computational power and memory. The Pi 3A Plus is based on a Cortex A53 with 4 1.4 gigahertz cores and 512 megabytes of RAM, which is big. Compared to a simpler architecture such as microcontroller, it's much, much more powerful. So running real-time DSP algorithms in a bare metal environment, by bare metal, we mean without an operating system, of course, on these platforms should allow for further optimizations by taking advantage of the Neon technology on the Cortex A processors, for example. That should help us get better audio latency as well. Some work has already been done in that direction by implementing the prototype of a Faust architecture for Circle, which is a C++ bare metal programming environment for the Raspberry Pi. Generated objects consist of kernels that can be placed on the Pi's SD card. MIDI and polyphony support has been implemented as well. The current toolchain remains relatively cumbersome, unfortunately, and that's mostly because of the use of the SD card, which has to be taken off the Raspberry Pi every time a new program is created. The system is currently completely static, unfortunately. Furthermore, the Raspberry Pi doesn't give access to proper audio inputs and outputs, and to sensor inputs, through a microcontroller, making it unusable in the context of embedded musical instrument design. So we're thinking of developing a bare metal kernel, turning the Raspberry Pi into a Wi-Fi hotspot, running a small web server, Faust programs will be sent to the Pi remotely using the system and will then be compiled using the on-the-fly embedded Faust compiler. In parallel of that, an RPI hat sister board, adding a microcontroller, and an audio codec could be developed. We've been exploring the idea of programming FPGA boards with Faust in the framework of the Cifala project, which associates INSA Lyon City Lab and Xilinx expertise around FPGAs to Faust with us at GRUM, basically. So we managed to run Faust DSP objects on a Digilent Zybo Z7 board, which is a development board hosting a Xilinx Zinc 7000 FPGA. This is currently done through high-level synthesis by compiling Faust program to C++ and then to an IP core. Specific Faust C++ backend had to be developed to make this possible. While our system already works, it is currently hard to control audio processing parameters in real time. Moreover, generated IPs are relatively inefficient, probably due to the use of floating points. Next steps consist in generating fixed-point DSP objects to further optimize produced IPs and improving the control of processing parameters. The results of these preliminary work are presented in a companion paper by Tanguy Risset, who will also give a presentation about that. We recently got awarded a research grant from the French Research Agency to work on this topic. So the FAST project, which you can see on the slides here, will be launched in March 2021. So we're really going to spend a lot of time working on this. All right, so finally, graphics processing units, also known as GPUs, have been increasingly used in recent years for real-time audio processing applications, taking advantage of their high degree of parallelization to run DSP algorithms that can be easily divided into multiple processing units, such as modal reverbs, for example. So we believe that Faust has a role to play in that context by facilitating the programming of this type of platform. We did some experiments already in 2010 by developing OpenCL and CUDA backends for Faust. At that time, results were not really convincing, but now that GPUs are becoming more and more powerful, and with better understanding of the class of DSP algorithms that can take benefits of their massive data parallelism capabilities, we do plan to work again on this subject in the future. So that's it for this presentation, folks. I hope you enjoyed it. If you have any questions, you can ask them to me now. Once the presentation is over, you can also send your question to my email address on michon@gram.fr. Also, the slides of this presentation are available at the URL displayed on the screen. Thank you.